Physics 2212, Lab 3, Magnetic Field of Permanent Dipole Magnets. The purpose of this experiment was to determine the impact of distance on the magnetic field produced by a bar magnet on and off of axis, as well as to compare the experimental values to theoretical values. In order to do this, we used a magnetometer and recorded the magnetic field values at different locations. We also utilized these distance observations to determine the magnetic dipole, and then we were able to use GlowScript code to determine the theoretical magnetic field on and off of axis. Using this method, we were able to get the result that the distance dependent N was equal to negative 2.92 meters, and the magnetic moment of the magnet, mu, was equal to 1.8 amps times meter squared. For this lab agenda, I'm first going to go over the main concepts, then the experiment, followed by the calculations and the GlowScript code, and then lastly the discussion questions. Physics concepts used within this lab is the concept of a magnetic field produced by a dipole, also the Biot-Savart law, which is the law that calculates the magnetic field produced by a current, specifically the form shown to the right, and then lastly that a bar magnet has a distance dependence related to its magnetic field, which also has a relation shown to the right. So for this experiment, I utilized the Teslameter app in order to be my magnetometer and calibrated it to be the true magnetic north according to the Earth's magnetic field. Using this, I was able to record the axis distance needed to get an x component with the magnitude of 20, 70, 120, 170, and 220 microteslas. These values are shown on the chart to the right, and I was able to get an average of all of these values. Out of the points I collected, I was able to create this plot, which is the natural logs of the x component of the magnetic field versus the natural log of the distance values. This plot will be useful when calculating the distance dependence in the magnetic dipole. Experimental procedure to determine the magnetic field off of the axis, I found the perpendicular distance where the magnitude of B net was equal to 100 microteslas. I collected 3 measurements at this location and found the average to determine the off-axis magnetic field. In the chart below, you can see the measurements I collected as well as how I observed the Earth's magnetic field to get the accurate B net. In the experiment, I observed that as the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased, and as it moved further from the magnet, it measured a near zero magnetic field for the x direction. To do the calculations for the on-axis magnetic field, I started by plotting the natural log of B versus the natural log of R and used that to solve for the distance dependence of the magnetic field using the slope equation. The slope equation in this form is the natural log of Bx equals the natural log of K plus N natural log of R. And in this formula, the slope, N, is equal to negative 2.92. I then used this natural log of K equal to negative 14.76 to solve for K, and then I used that to solve for the magnetic dipole moment, once again using the distance formula of B bar equals K times R raised to N. Rearranging this and inputting the equation for B bar, I solved for mu equal to 1.8 amperes times meters squared. Next, I coded my GlowScript code, and the goal of this was to calculate the magnetic field of a dipole in order to compare the computed field to my experimental measurements off-axis. In order to do this, I used a function to calculate the field within the code, and I visualized the experiment by setting up a cylinder at the origin to represent the magnet and used arrows on axis, perpendicular to axis, and 45 degrees off axis to represent the magnetic field. Out of code, you can see I created a magnet at the origin using a cylinder and then created a function for the magnetic field using the Biot-Savart law. Next, I created an arrow scale so that the arrows I created would be visible within the results screen, and then I moved on to determine the observation locations that I wanted the 2 arrows on axis and the 4 perpendicular arrows to sit at. Then I proceeded to actually visualize the 2 arrows on axis using those observation locations, and I proceeded then to create the 4 arrows perpendicular to axis, and I used the exact same method except using different observation locations. In order to visualize the magnetic field at the 45 degrees off axis, I used this perpendicular distance and once again created arrows using that distance and the B scale so that it would be visible. Here are the results I obtained from my code, and in the screenshots you can see the frontwards view and also a sidewards view where you can view all 4 of the perpendicular arrows and the 2 axis arrows, as well as the corner 45-degree arrow. You can also see my magnetic field axis and perpendicular fields produced at the bottom. Experimental value to the theoretical value of the magnetic field along the 45-degree axis at 0.178 meters, I found that my experimental value was not significantly different from the theoretical value except at the z-value. Questions, I determined that had I not compensated for the magnetic north, the x component of the magnetic field would not have started at 0 teslas, so that the final answer would have been the magnetic field of the bar as well as the Earth together, and that the distance dependence as well as the magnetic dipole would end up being different. And then also that if I were to stick 2 magnets together, this would increase the magnetic field that I observed, but the direction would still be the same. In conclusion, by using knowledge of magnetic fields as well as the Biot-Savart law, I was able to determine the distance dependence of the magnetic field to be negative 2.92 meters and the magnetic dipole moment to be 1.8 A times m squared. From this experiment, I concluded that the magnitude of a magnetic field due to a bar magnet decreases with increasing distance.